Why didn't it make sounds? I think it's recording. It says it's recording. I will have to trust it. I didn't hear the normal sounds it gives me, but just to double check, you can hear me, right? Okay. Here we go. So with number 32, it wanted you to, or was it 31? It was 31, wasn't it? Not 32. Okay. For number 31, you were supposed to evaluate the integral and interpret it as the area of a region. So let's draw a graph of sine. But we're only looking at the integral from 0 to pi over 2. So that's just this little bit of it. Then for cosine 2x, when you go to draw that, do you remember that multiplying the x inside really is telling you what to divide the normal cycle by? So the normal cycle of cosine is 2 pi. Divide that by 2, and you get that it will go through its entire cycle in just a pi amount. So it does I start at the top, but at pi, it's done with the cycle already. And let me erase this because it's really poorly drawn there. So the cosine I still had the erase on, didn't I? Sometimes you just have to laugh at how things are going. Which I suppose is 2020. It's a joke all on its own. Some kids doing comedy sports in the future, they're going to make a whole joke out of just going up to the mic and saying 2020. All right. From 0 to pi over 2, I am looking at in between these curves. So as far as drawing a picture of the region, that would be it. Now, if I'm going to solve this area, I can't integrate with absolute value. So I have to look at when I go from 0 to the first intersection point, which I'm going to need to find, cosine of 2x is larger than sine x. And then I'm going to start again at this intersection point and go until I reach pi over 2. And during that time, it switches and the sine 2x, or sorry, the sine x is the larger function. So to find the intersection, I have to set these two equal to each other. And I'm hoping you remembered that there are trig identities for cosine 2x. Did you remember that? And perhaps you looked them up. And there's a trig identity for cosine 2x. There are actually a few choices when it comes to cosine 2 theta. And I'm trying to remember off the top of my head, I believe, and you can tell me if I'm wrong, 1/2 times 1 minus cosine squared theta. No, that's for sine 2 theta. Cosine, maybe I should look it up to be on the double safe side. Or does someone have the identity already? I can look up trig identities because I don't want to mess that up and give you the wrong trig identity. Okay. Where are they? No. Ooh, that has a lot of trig identities on it. How do I make that bigger? I don't know, but I will bring it over. Okay, so that's right. Now I remember. These double angle formulas were what we were looking for. Cosine 2 theta is equal to 1 minus 2 sine squared theta. That's the one you want to use. You see you have three choices. I know I'm trying to solve an equation that involves sine that isn't having the double angle. So if I take that cosine 2x and I use the identity that involves sine squared, not the identity that involves cosine squared, and not the identity that involves both, but the one that brings in a sine squared, that's the one that I want to use. So 1 minus 2 sine squared. And now, if you noticed, I had to look up that trig identity, and I've been using these for years and years and years. You know, you memorize trig identities, you have to memorize right before a test. They can stick around in your head for years at a time and then disappear if you don't use them. But all you have to do is know how to look them up. And when you notice that that you have a problem of a double angle, you look up double angle identity. So the sine x I'm going to leave. This is the equation I'm trying to solve so that I can find the intersection. And what I saw was this was a double angle where this was not. So I looked up double angle identities. But if you're not sure, you can look up both double angle identities and half angle identities, and they can work with you. So I'm going to substitute for my cosine. Actually, I should use a different color. Oh, well. I'm going to substitute. Happy Monday. That cosine 2 theta, I'm using that formula to substitute right here. So I have sine x equals 1 minus 2 sine squared x. And what I have is a quadratic. I'm going to add 2 sine squared to the left side. The left side already has sine x, and I'm going to subtract 1 over to the left side, and then I can factor. Now, if you don't see the quadratic factoring through sine, you can always go, this is 2s squared plus s minus 1, and use just a letter instead of an entire function, and people find that they have an easier time thinking through the factoring through the letters rather than the functions. So this is going to factor as 2 sine x and a sine x, or if you're over here, 2s and an s. And then to get that positive middle term, I need this to be a plus 1 and this to be a minus 1. Stop. Now, this gives me either sine x is equal to 1/2 or sine x is equal to -1. And if I look at the fact that these actually intersect quite a few times if you look at the graph, I'm looking for the very first positive angle. And sine x hitting a value of 1/2 is going to be the first positive angle. And that's going to be pi over 6. So all that work just to get pi over 6. You probably could have guessed that and checked it by plugging it in to the equation and see that it actually does work. But anyway, now it's a matter of integrating. Do you want me to take you through the integration? Okay. So I'm going to put a big giant 1 and a big giant 2. So big giant 1, that first integral. I am integrating cosine 2x. So I have to do a u substitution. That's a very good question. Do you have to know the trig identities super well for the AP test? I have asked that question before to College Board, and they said basically that they were fair game but unlikely to show up, if that makes sense. We'll be looking at trig identities, and you can always just kind of go over your trig identities right before the AP exam just in case, but I wouldn't worry about it too much. The trig identity you want to know is sine squared plus cosine squared equals 1. That's the most important one to know. But honestly, you can probably be okay on the AP test without having them memorized, but you can't hold me to that because I don't write the AP test. So basically the idea is it's a good idea to know them, but it's doubtful that it's going to matter. That's the best I can tell you. So when I integrate cosine 2x, I have to do a u substitution. And let me point out to you something. The first integral I'm solving is this one right here. I can separately integrate over this subtraction sign. I need to solve this integral through a u substitution, but I don't want to use that u substitution on this. And I found that sometimes people get confused and they feel like a u substitution has to be used for every single term in the integrand. You can separate these two. Now, I took the constants off. Let me put them back on. So you can do this quickly. You don't have to show all the work that I'm showing right now. But I want to make sure you are clear that you can separate these into two separate integrals. Then do a u sub on one of them and don't do it on the other. For this one, I have u equals 2x. The derivative du dx is 2. When I multiply dx to the other side and I divide 2 over to the du, I get my substitution for the dx. Why only one u sub? Right now, I'm only integrating this function of this integral. When I go to this one, I'm going to have to do it again. I'm going to do one of these two integrals and leave the other one for you to do. So you'll do a u sub on this part in the same exact manner that I'm doing this right now. I'm just going to solve integral number 1. So now I have the integral of cosine u, and then the dx is substituted with a du divided by 2. If I use limits, I cannot use 0 and pi over 6, but what I can do is I can use this. When x is equal to 0, I plug it in, u is 0. When x is equal to pi over 6, I plug it in, u is equal to pi over 3. And now I don't need to go back to x when I solve this integral. And I still have a second integral over here. I still have this separate integral of 0 to pi over 6 of sine x dx. So I take my 1/2 constant multiple that comes from here. I integrate cosine and I get positive sine u. And then the sine of pi over 3 is root 3 over 2 minus the sine of 0 is 0. Then for this one, I'm dealing with respect to x. So with respect to x, the integral of sine x is negative cosine x from x equals 0 to x equals pi over 6. I'm going to bring those two negatives together. Actually, I'll keep it there. Then integral has already been taken, so I'm ready to plug the numbers in. For pi over 6, the cosine is root 3 over 2 minus the cosine of 0 is 1. The pi over 3 comes from taking the pi over 6, plugging it into this x, and getting that u is double pi over 6, so it's pi over 3. So that's solving the one integral. You still have to go through and finish the problem and solve the other integral. Now, I'm actually starting to think that it would be a good idea if I went to volume. And then I'll do more of these problems another time. Actually, later today, I'll just make a bunch of videos for you. All right, let's look at number 8, rotational volume, number 8. I have the function 1/4 x squared. So I'm going to try and draw a flatter looking parabola. And the function 5 minus x squared. And let me change your color. Well, you know it looks symmetric. So I am looking at this entire region is being rotated about the x-axis. I need to know the intersection points. So setting the functions equal to each other. 1/4 x squared equals 5 minus x squared. When I add the x squared over here, I get 3/4 x squared. No, I don't. I get 5/4. So I have 5/4 x squared equals 5. Then I multiply by 4/5, and I get x squared equals 4, so plus or minus 2. We are taking this region and rotating it about y equals x. I'm going to draw the radii. The radii are from the axis of rotation to the function furthest. There's my big R. My little r is from the axis of rotation to the function that is closest to the axis of rotation. So there's little r. Then I want to realize that I'm creating a bunch of disks. And then with both of these radii together, I'm creating washers. The area formula of the washer is pi times the larger radius squared minus pi times the smaller radius squared. There's my area formula. Now, because the radii are perpendicular to the x-axis, these are dx integrals. So the dx is going to take this two-dimensional formula up one dimension to 3 dimensions. And the x coordinates where it exists is -2 and +2. So now I have the variable I'm working with is x. I've gotten the area formula using geometry. Now I get into the particulars on the XY plane. The actual length of each radii. For the longer radius, the top y value is y equals 5 minus x squared. The bottom y value is 0. You do not have to write minus 0. For the smaller radius, the top y value is following the parabola 1/4 x squared, minus the bottom is following 0. You don't have to write minus 0. So that setup, then integrated by hand, will give you the volume. And do you want to see this integration done, or you're good enough? So go on. Okay. So that was number 8. Now let's take a look at number 16. With number 16, I have the function y equals x, going through the origin. And I also have the function y equals root x. And if you think about it a little bit, you'll realize that they intersect at 1, 1. But I'm rotating this about x equals 2. Now, here's a wonderful thing. The AP test will say about the vertical line, x equals 2. They used to not say that. I noticed one year they just started putting that in. I think they got very frustrated with students making that particular dyslexic error. So, as I set up for disks, I need to draw radii that are perpendicular to the axis of rotation. My radii are then, let me change color on that. From the axis of rotation, then it goes to the furthest of the two functions. That's my big radius. From the axis of rotation to the closer of my two functions gives me little r. Now, when my radii are going horizontal instead of vertical, my tiny cuts are little tiny vertical values. That means this is a dy integral. So with a dy integral, I need to know what the y values are of intersection. Even though the x and the y are the same in this case, I want to overemphasize we are looking at the y values, y value 0, y value 1. Now, the geometry, I need an area formula with respect to y. That area formula is still going to be the pi times radius squared minus the pi times radius squared. Are any of you reaching the point where you're just pulling the pi out of the whole thing? If you do that, I give you a huge warning. It is very easy, and I am telling you, you'll be shocked if it ever happens to you. It is very easy to accidentally do this. Be vigilant. In fact, I prefer to keep you using the formula in this manner to force this not to happen to you, because I cannot explain to you until you experience it how easy it is to accidentally write it wrong, and you know better. And the problem is that usually happens to people for the first time on a test, because the test is when your brain's going all wonky because you're nervous. And this is a very common error. It's so common that in multiple choice, this is always one of the choices when they give you multiple choice problems with this. So I'm going to keep writing it this way, but I want to really, really warn you about this. You have no idea how easy it is until you do it and look at the evidence that you actually did do it. All right, so I'm going to write out pi, big R squared, minus pi times the inner radius squared. I've got my area formula, and now I'm putting my dy back on. Now, I need to get this horizontal distance for the outer radius. I need a right x and a left x. The right x is x equals 2, where the line is. The left x is using this function, but solved for x in terms of y. So if I square both sides, I now see what x is equal to in terms of y. So x coordinate 2 minus x coordinate y squared. Then for my inner radius, I also need to look at, it's a horizontal distance. I need a right x and a left x. The right x is 2 again. The left x is x being equal to y. This is the integral that you need to have set up. And when you do go to solve this integral, realize that the key issue is you have to expand that binomial squared correctly, and you have to expand this binomial squared correctly as well. So real quick, just to remind you, when I square them, I get, for the first one here, 4 minus 4y squared plus y to the 4th. And then this one is 4 minus 4y plus y squared. Then you can integrate each of those using the power rule. Now, I'm going to move on to a next problem just to get through as much as I can with you today and help you out. And this is being recorded, so you can look back on this later. And now for number 18. With number 18, we have y equals x, y equals 0, x equals 2, and x equals 4. And what they are expressing, now I realize that this actually cuts it up into more pieces than you would, it's not clear. Know that when they give two x coordinates in a row like that, they're basically saying between them, the textbook would do a better job if it said this. That's what it is actually meaning. On a test, it will be clear. So this region is rotating about the line x equals 1. So there's x equals 1. And as I prep this, I want to draw my radii. Ooh, does anyone see? Right here, I'm going to draw a vertical line there. You actually have to find two volumes separately. Let me explain. If I go to draw my outer radius from the axis of rotation to the furthest spot, and I'm going to draw a couple of them. My inner radius is from the axis of rotation to the closest function. That closest function changes at this y value. Now, if I'm doing this purely by integration, then I'm going to set up two integrals. And ultimately, I'm going to add those two integrals together. And I need to also know what this y-coordinate is right here. So this is the y-coordinate. Well, okay, that's not too bad. I'm looking at, nope, I highlighted the wrong thing. X equals 2 and y equals x are intersecting to create that point. So basically that's y-coordinate 2. Why are we adding? You know, let me get the whole thing set up and then you might see why. Because this one's really a bit tricky as to why you're setting up the integral the way that you are. I'm cutting it up right here. And I'm first taking these little sections and rotating that about the line y equals 1. The radii are horizontal. When I have horizontal radii, I am working with a dy integral. Let me just go ahead and keep using orange for that. The y values are from 0 to the intersection point 2. While I'm in between these two y values, I have a pi times big R squared minus pi times little r squared. And then the dy, I already have that written. Whoops. The radii are a horizontal length. In fact, the radii are a constant. For my bigger radius, my x right is 4, my x left is 1. So basically, I'm just having a constant radius of 3. For my inner radius, my right x is 2, my left x is 1. 2 minus 1, or basically a radius of 1. So this much of it is going to create the volume of this section. Now I've got to change to looking from y equals 2 to y equals this intersection, which is 4. And it's 4 because it's the intersection of the line x equals 4 with the line y equals x. So starting at y equals 2 and going to y equals 4, it's again a dy integral because my radii are horizontal. I have my two radii drawn up here. I've got pi big R squared minus pi little r squared. For this radius, the right x is 4, the left x is 1. I again have that it's just a constant 3. But now finally for something a little different. This right x coordinate comes from the line y equals x. So that right x is equal to y minus the left x is equal to 1. So that's a lot of work to go through to set up the volume by calculus. This would probably be easier to do using pure geometry. But this is what it would take to properly set up an integral to find that. So does it make sense now? I had to find two integrals because, and pay attention if it didn't make sense to you. My left x changed the function that it was following. So if I'm looking at this region right here, and if I were to just draw inside the region little horizontal lines, I can see that the left side changes the function it's on. And that ultimately causes my inner radius to change. The only difference between these two setups is that as y goes from 0 to 2, my inner radius has its right side following x equals 2. But when I am between 2 and 4, my inner radius has a right x that is following the line y equals x, or x equals y. For that one small thing, I had to set up two integrals, find the individual volumes, and then add those two volumes together. So I'm hoping that makes sense as to why that's set up this way. I'm going to leave the integration to you. And then I'm going to come back over to these problems right here. Come on. Yeah. When I look at the formula here, I see pi and I see a squared on my cosine. That tells me that most likely I'm dealing with a radius of cosine where the area formula is pi times that cosine being squared. So most likely, I'm going to draw a cosine graph. I'm looking from 0 to pi over 2 only. Now, if that is the radius, if these little red lines that I drew represent the radius, then I am going to rotate it about the x-axis so that I'm getting a solid shape with this radius, giving me one of these discs. That is not the only possible region, and it's not the only possible axis of rotation, but it's most likely the one who's going to be set up in this manner. So it asked to each and just describe the solid. So the solid is the region bounded by, I would say it was bounded between x equals 0 and pi over 2, bounded also by the x-axis and bounded by cosine x. So this creates the base region that is then rotated about the x-axis. And so that's problem 41. With 42, that's looking at dy, but it's trickier because you don't see an obvious function being squared. You know your basic formula is pi times some radius squared. So who do I square and end up getting y? And you realize who do you have to square to get y? Yep, square root y. So most likely what I'm dealing with is the function x equals the square root of y. X equals the square root of y. I've got to actually kind of think of that as, wait a minute, that's not my square root graph. That's actually, if I square both sides, the right half of a parabola only. So this is the function x equals the square root of y. Now, the variable of the integral is y. The limits are 2 and 5. So I'm going to find y values 2 and 5. And this is looking at a region in between y equals 2 and 5. It is bounded by the y-axis. It is bounded by the graph of x equals the square root of y. This region is rotated about the y-axis. And I want to say again, there is more than one possible correct answer, but this is the one that is most straightforward. Okay, now we have a little bit of time to go back to area. So let's take a look at number 19 from area. You know, maybe the muted mic saved some people from getting too far behind, because I was going to go into the next type of volume and then review, but I had to, basically, if you look at the calendar, Monday and Tuesday are flipped around is what's going to happen. Instead of taking you further into volume and then reviewing, I ended up having to review first to deal with the microphone problem. And to be honest, I actually debated whether to do that way anyway. It's like fate kind of told me which way to go. All right, so I need to think, how do I graph this? This is a sideways parabola because it's an x equals y squared version. You can see that it's a positive leading coefficient, shall we say, so that it opens to the right. There's no addition, so it's definitely opening with a vertex at the origin. And then if you want more accuracy based on that multiplication by 2, you could plug in a number, like plug in for y plus or minus 1 for y. If I plug in plus or minus 1, I'm going to get an x-coordinate 2. So that kind of gives me an idea of how that multiplication did it stretch, compress. Now, the other one, 4 plus y squared, it's another x equals y squared. Now, it does have an addition. Without the addition, the vertex is at the origin. What I see easiest to deal with is you want addition subtraction to be directly to a variable. If I subtract the 4 over, I can see a direct, excuse me 1 second, that's an equal sign. There we go. I can see that that's telling me a movement right 4 units. If I ever have addition, subtraction in a parentheses with a variable, what you can ask yourself is, what can I plug into that x to make that parentheses become 0? And that will tell you the motion of the graph who didn't have the plus or minus of that number. So I am moving right 4 units. 1, 2, 3, 4. But this parabola opens normally, and that's going to cause them to actually intersect each other, even though it's opening to the right. I can see that there are some intersection points, and the region, this would be the region it's describing. And in number 19, which axis was it rotating around for 19? Was that the y-axis? You guys have that in front of you. Was that the y-axis? I didn't write down. If you don't know, I will have to go check. 19. Wait. Area. That's why I'm confused. Sorry, wrong section. This was just area, so I'm not having an axis of rotation. I'm going to erase this down here. I need to know my intersection points. To find the intersection points, it's going to be easiest if I set the two x's equal to each other. So x equals 2y squared and x equals 4 plus y squared. Then, come on, erase. I subtract the y squared over. I subtract the 4 over, and I can see it's plus or minus 2 on the y. I know this is not to scale, but I would really like to find my area by a horizontal rectangle, not the typical vertical. So I will set up a dy integral from y equals -2 to +2. The right x coordinate is 4 plus y squared, minus the left x coordinate is 2y squared. And then solve that integral, and our time is up. So let me stop that